あ、これそういえばスライドのあれってポチポチなんだっけ。あ、ありがとうございます。Yeah, so hello everyone, and thank you, Mayuko, for the introduction. So my name is Yugo, and I'm a second year Ph.D. student at the University of Tokyo, which is actually just 15-minute walk from here. So if you just walk up the hill, yeah, there is our campus. So yeah. And I observe what's called exoplanets. So basically they are planets outside of our solar system. So in our solar system, around the sun, we have, our Earth, and then we have, Venus, Uranus, Jupiter, Saturn. Yeah, I forgot the order in English, but yeah. So these planets, but if we look at our sky, we see a lot of other stars, and those stars also host these planets, right? And so we call them exoplanets as short for extrasolar planets. And as my hobby, I also really like baseball. And this is a picture of me and my brother at World Baseball Classic in 2023 in Miami. So if any of you guys are into baseball, so this was like a very big baseball World Cup thing that was going on in Miami. And yeah, I was on TV, and I didn't tell anybody that I was going there, but people like my friends just texted me, do you happen to be in Miami watching baseball right now? Because I think I see you on TV. And yeah, so that was me on TV. Yeah, 2 years ago. And I'll be in Miami next year as well. So when the tournament's coming up next year as well. Yep. Okay. And so she gave me a little bit of the introduction about my background. So I have a bachelor degree in liberal arts and also in communications. So basically I did journalism back in my undergrad. But why am I doing astronomy all of a sudden right now? And so this is a little bit of a background. So on a COVID day, so when we had nothing to do, I was stargazing, but not stargazing outside. I was stargazing with a YouTube channel because we couldn't go outside. So I had my lights off, and with my family, I was watching stars on the YouTube screen. It's a live cam from Hawaii with the Subaru telescope. They have a webcam there. And I was watching all these stars, and I'm like, I have all this time, and the stars just look too beautiful to be just hanging around. And I thought maybe I have a year, so if I studied really hard, I might be able to do it. So I just decided on that day to just really put the effort and study for 1 year to get into a program. And luckily, University of Tokyo was there to offer me a program. So now I am in Komaba studying exoplanets. So that's a little bit of my introduction. And so now I would like to introduce you guys to exoplanets. And so I would like to start with this little quiz here. How many exoplanets are discovered to date? And I will give you these 4 numbers. There are 4 options. So who thinks 56 exoplanets so far? Okay, so you guys are... What's the definition of exoplanet? Oh, okay. So exoplanets, basically, we see all these stars out in the sky. And so basically planets that are orbiting stars other than our sun. So we call them exoplanets. So how many of those exoplanets do we think?
They're orbiting other stars?
Other stars, yes.
They are orbiting the sun?
They're orbiting other stars. So they are not orbiting our sun. Yeah. So how many of them do you think we have found to date? 56? 56?
No.
Okay. So if you guys picked 56, that's actually the number of political candidates who stood for mayor of Tokyo in 2024. So that's obviously the wrong answer. And who thinks it's 1,025? Okay, so you think maybe 1,025? That's actually the number of Pokemons out there. So that's wrong as well. So maybe the other 2 options. Who thinks it's 6,045? Okay, 6,045? Yeah, okay, 6,000. Who thinks it's 21,533? Okay. So the correct answer is 6,000. And 21,000 is actually the number of 7-Eleven in Japan. Yeah, so we don't have as many as 7-Elevens. We don't have as many exoplanets as we wished, or as many as 7-Elevens, but we do have 6,000. And counting, and counting. We recently just passed 6,000, so which is a feat, actually. And so I would like to start by talking about how did we even find the first ever exoplanet. And so we give you, so I put here this little animation here showing you, or I'll go step by step to explain how we found the first exoplanet. You guys might have heard of this already, but I'll just go step by step. So think of it, we have the observer here. And if you're looking at a planet and a star orbiting, if you're looking at a planet orbiting a star like this, we'll find that the planet is actually not orbiting around the star, but the star is also orbiting around the center of mass that's created by the star and the planet. So a good analogy to this is if during your childhood you had your dad spin you like that. If you think about it, the dad is not spinning like that. So there is this little center of mass that's going on. So the axis of spin is not exactly here, but it's more like here, right? So there's this wiggle going on in the star as well. Yeah, so the planet and then the star, but the star is also wobbling, right? And so actually this is not a real footage of a dad spinning the daughter. I told ChatGPT to create the video, dad son spin video, and it came up with it, which is kind of scary. But yeah, anyway, so this is an image of what's going on. But so the point is, if we catch the wobble of the star like this, we can definitely think that this wobble is happening due to a planet orbiting the star. But how would we even observe such a wobble, right? It would be good to know the speed of the star as it's being wobbled. So maybe if the star is going this way, it's accelerating along our line of sight, and if it's going that way, if it's coming to us, the speed of the star is negative, so it's coming to us, right? So if we can measure the speed of the star with respect to our line of sight, it will be great. But how do we measure the speed is the question. And feel free to stop me anytime if you have any questions.
Yeah.
Yes.
Why we cannot observe the light of the planet itself?
Yes. So if you think about it, so thank you for the question. And the planet is really dim. It's really dark compared to the star. So actually, the star is about how much more luminous? It's basically the planet is basically invisible in the existence of a planet of a star so nearby. So basically, we cannot observe the planet directly, but we can only observe the planet indirectly through the existence of a star. Yeah. Yeah.
You're speaking about the concrete planet, right?
Yes.
Does it have a name or a number?
Oh, so this is just in general. So this is how we would find a planet in general. So if we had a star and a random planet here, the star will be wobbling.
Why
Yeah.
can't we just
Yeah.
why can't we just try to spot a black spot?
Okay. So so that's another way to find a planet, and that's called a planetary transit. And the reason why I'm introducing this first and not the transit is because this is how they found the first exoplanet, but a few planets after, and we are actually spotting more transits, and transit is actually the main method we find exoplanets today. Yeah, thanks for the question. So how do we measure the speed of the star that's wobbling, right? So an analogy to this is the Doppler effect we observe. We kind of know from, for example, our F1 cars. Because we know what engines sound like, if the cars are coming like, then we would know how fast it's coming to us, and then how fast it's receding from us, right? That's because the wavelength, the frequency of the sound is changing as it approaches us and as it's receding from us. And it's important that we know the important thing is that we know what engines sound like in the first place, so we have a reference point to compare the sound of the engine that's changing over time. But with stars, we're not hearing their sound, but looking at their light, right? The light that they emit. So what do light from stars look like? If we think about like a prism and like a rainbow, we break down the light that we're observing from the star. It looks like this, basically. It looks like this if the core of the star, and then if nothing is in the way, and then this is what we would observe, like a pure rainbow. But then, since we have these like little outer layers of the star with all these different elements in them, for example, helium, or no, hydrogen, there would also be heliums, but atoms in the outer layer of the star would absorb light at specific wavelengths, absorbing the light, meaning it wouldn't reach us. So there will be specific distinct lines that are caused by these atoms actually absorbing the light at specific wavelengths. So there will be, there will be these lines. So what actually happens is that as the star is being wobbled, these distinct lines cause these Doppler shifts that are also happening for our Formula One cars. And then so the lines are what is actually wobbling. So if we break down the light of the star that we're observing with these prisms, we can actually observe the planet, the wobble that's 80s. And this was the first candidate exoplanet they had in 1992. So So this is the paper that came out in 1992 by a professor named Gordon Walker. We'll talk about him later, but so this is exactly what he observed, right, 30 years ago. And he found a periodic variation, like a wobble of the star, exactly, happening at an orbital period of 2.5 years. So basically, he thought he found something that's wobbling the star at an orbital period of 2.5 years. So compare that to our Earth, that's orbiting the planet, the sun in 1 year. So this one had a wobble with a period of 2.5 years. And the size of the planet that he thought was wobbling the star was about the size of Jupiter. But then if you think about the orbital period of our Jupiter, it's about 12 years. And for our Saturn, it's 30 years. So at that time, he was expecting something like the orbital period of like 12 years, or maybe if not longer, for these giant planets to exist. So the fact that he found these Jupiter-sized planet at an orbital period relatively shorter than what he expected, he was in a little bit of a self-doubt.
May I ask something really nerdy?
Yeah.
Isn't this only this wobbly, like what we call it, symmetrical wobbly graph only true if the distance stays the same? If the distance between the observer and the object stays the same, that's obviously this kind of like cosine-like curve will be observed as, you know, as if the object is wobbling here. But the problem is Earth is also moving, and so the observer and the objects move quite independently. So
Yes.
this symmetrical pattern.
Yes. So that's what you call a parallax. So if the Earth is moving, so because the Earth is moving, the position of the star will change in time. But since we are pointing at that star, so that would become a problem if you're measuring the absolute position of the star as we see. So for example, one day the star was there because the Earth is moving, the other day it's there, then that will be a little bit of a problem. But since we are pointing to that exact position of the star as it's moving in our sky every day, so that it would be a problem for other measurement methods, but for this specific observation,
I guess you can set a baseline.
Yeah. Yeah, so basically, he was in a little bit of a self-doubt. And what he did is that in this paper, he didn't come to a conclusion that this was a planet. So if you see the title of the paper, he says rotation or planetary companion. So he thought it was, he eventually concluded that this was not a rotation, but the wobble of the star itself, its self-contraction and expansion. And he didn't say that it was a planet. So this is an article that came out maybe about 20 years later, where he recalls this memory of retracting his conclusion about this discovery of a first exoplanet. You know, he said he had initially written the paper as it being a planet, but then there's this random dude that came in quite recently, and he's been sitting in the office for so long, and he was like, I think this is just contraction and expansion of its own star. And he was like, yeah, I doubt myself too much to push myself further, so I'll just probably change the conclusion a little bit. That's what he basically said. And so he missed the very first discovery of an exoplanet. And then he still kept searching, you know. And then 3 years later, he published this paper, which said, I looked for everything. I looked as hard as I could for maybe about 12 years, and I couldn't find anything. So probably there aren't Jupiter-like planets out there in our solar system, outside our solar system. So that was a very pessimistic paper that came out in 1995. But what also came out in 1995, just 9 months later, is this Nobel Prize winning paper that said a Jupiter mass companion to a solar type star. So it's written by another team. So this guy was from Canada. This guy was from Switzerland. So it's a Swiss team. Just two people, actually. One graduate student and one professor. Came out in Nature. And they said, a presence of a Jupiter mass companion to the star 51 Pegasi. And believe it or not, the orbital period to this planet was just 4 days. So remember, Gordon Walker had too much of his self-doubt in a planet whose orbital period is supposedly 2.5 days, which actually turned out to be true, and it was a planet. But these guys just said, yeah, this is a planet, 4 days. I don't believe it, but yeah, you guys, I cannot find a better explanation, so I'll just put it in a paper. So that's just what happened. Just 9 months later, and this won the Nobel Prize in 2019. So if you look at the article, it said how Canada missed its moment of glory. Yeah, oh, I feel for him. Anyways, and one little thing that just that happened after this discovery winning the Nobel Prize is also the name of the road where the observatory is located, where they did their research, is called 51 Chemin, I think, is the French word for road, and Mayetz was the name of the road. But they renamed the road afterwards to Chemin Pegasi 51, which comes from the star that had the first exoplanet discovered, which is pretty cool. Anyway, 30 years later, this is the current map of exoplanets, all 6,025 of them. So we have the orbital period on the x-axis and the planet mass on the y-axis. And here we have 51 Peg B. And we have more than 500 of these similar planets discovered. And they are known today as hot Jupiters because orbital period of 4 days, if you think about it, the Earth completes one orbit in 365 days, but then these guys complete their orbits in like 4 days. And if you look at it, 51 Peg B is not even the shortest orbital period planet these days. We have these planets at orbital periods of even less than 1 day. So these planets are basically like really, really hot, right? Because they are so close to the stars. So that's why we call them hot Jupiters. But then the age of the impossible planets begin, right? So because they didn't believe it, because something so giant, so nearby couldn't exist in planet formation theory at the time. So I'll give you a brief introduction about how we think planets form. So we start from like these very, very small dust particles, and these stick to each other to form bigger parts, or what we call pebbles. And then these just keep snowballing to become planetesimals, and then we have icy planets. And then if there is surrounding gas and the gravity of these icy planets is big enough, it would eventually become gas giant planets. But then the problem is that if we are so close to the star, these icy dust cannot exist because it's just too hot and they would just evaporate. So we need so they exist, but we need some other better way to explain these impossible planets. So what's a good idea to explain the existence of hot Jupiters if they cannot form where they form? So this is a little quiz again. Number one is they migrate. Number two is conspiracy theory. They don't exist at all. And the answer is, of course, that they migrate. So they form outside and they somehow migrate. Yep. Sorry for this dumb quiz. Anyway. Anyway, so here comes the migration paradigm. So we think they cannot form where they are found. So we think they form outside and somehow migrate inwards. And we have two big theories about how these planets migrate. And one we call high eccentricity migration. So if planets form outside and there are these companion star or planets, so nearby planets or stars that's gravitationally influencing the orbit of these to-be hot Jupiters, and they'll just disturb the orbit so much that the orbit will be so elongated, what we call high eccentricity, and then eventually when they approach near the star, they will circularize the orbit to a close one, so it goes 1, 2, 3. So this is high eccentricity migration. The other one is a little bit more straightforward. We have disk migration. So when the planet is forming still, there is still the remaining disk, right? The protoplanetary disk that's surrounding the star. And then we have the planet slowly kind of like drifting inwards, kind of like being swallowed, going inwards, drifting through the disk. So this is disk migration. And so we do have observational evidences for these two migration theories. And for high eccentricity migration, so high eccentricity, again, meaning how elongated so the observational evidence we find for this migration theory is that we have discovered some planets that are on very elongated orbits with high eccentricity. So we characterize how elongated the orbit is on a scale of 1 to 10 in a quantity called eccentricity. And 0 means the orbit is completely circular, but a value larger than 1, then the planet will be ejected from the orbit. And we have these two very stereotypical planets with very high eccentricities, for example, 0.93 or 0.94. So these planets have like extremely elongated orbits that they might just be like, ejected from the orbit if it's perturbed even more, but they just happen to survive. And the fact that we do find these elongated orbits suggests that there must have been some kind of stellar or planetary interactions that cause these very elongated orbits in the first place. So this is one observational evidence we have for high eccentricity migration. And how do we find these eccentric planets? So I would like to spend a little time to explain as well. So since we explained how to find planets in the first place, this is a very kind of like a applied version of it. So think about an elliptical orbit. If you remember from high school, there is something called the Kepler's first law, and which basically says that in the A and B, close to the star, you have to go really fast to sweep out as much area as it does, spending time here. So since point B is very far from the star, you can travel just this much and occupy as much area as A is occupying, but a planet must sweep the same amount of area, A and B, in the same time, meaning that when the planet is passing this arc around A, the planet must go really fast. And what happens is that if we observe the velocity as I explained just now, when it's passing around the arc A, the speed of the wobble of the star just goes really, really fast here, like that, and then it slows down around the arc B here, like that. So we would not find sinusoids, but we do find like these very distinct curves, and that's how we identify these eccentric orbits. Anyway, we also do have observational evidences for disk migration. So if we think about it, high eccentricity migration is very, very violent, right? So it would be caused by these very disturbed orbits, and it would almost certainly destroy other planets nearby if they just happen to orbit very close. So basically, around hot Jupiters, if everything is formed by high eccentricity migration, we wouldn't expect to find nearby planets. So for example, in our solar system, we have Earth, and then we have other planets like Venus, Uranus, and so on. But basically, the high eccentricity migration prediction is that there would be no companion planets nearby. But then we do find a couple of these planetary systems. So here we have a hot Jupiter, and then we have friends here orbiting interior to the planet, and then we also have friends orbiting exterior to the planet, and then so on and so forth. We do have some planets that are hot Jupiters that are orbiting together with some friends. So this would be an observational evidence for disk migration. So which one happens more often? And this is a question we're still trying to answer, and I'm doing some research on this. But 30 years later, we're still pretty divided on what the dominant channel of migration is for these hot Jupiters. And I would also like to spend some time thinking about what happens to these hot Jupiters, right? So even after successfully migrating to the current orbit, think about this planet that's so close to the star, and with extremely short orbits, hot Jupiters evolve even after successful migration. So what happens if you, maybe you've heard of this, but so I would like to start by elaborating on tides on Earth. So if you've heard of tides and how the moon is responsible for it, this is a schematic image of how moon is raising tides on our Earth, right? So we have high tides where the ocean level rises. And what happens with tides is that we're not only, the orbit is not, the ocean is not only rising, but it's also affecting the moon. Namely, the orbit of the moon is also expanding very, very slowly, about 40 millimeters per year. And to give you an intuition, I would again introduce the dad here. So if we think about it, if you're spinning something really, really fast, if you're trying to spin up, for example, your child here, it would probably feel like you're giving out energy. So you're trying to spin up, or you're trying to give energy to spin up the child. So you're essentially slowing down, and then it's kind of weird to say the orbit, but the orbit will be like kind of expanding, right? So I think you can kind of imagine what happens if you're trying to spin up. So that's what's happening. So the moon is raising tides, and the moon is also expanding in orbit. What happens to hot Jupiters is actually the exact opposite. They're so close to the star that the orbit of hot Jupiter is faster than the spin of the star. So it's the opposite of what's happening here. So it's like your child is trying to drag you. So it's like your child is trying to drag you and trying to spin you up. So if you're trying to stop that from happening, you would put energy in, and then as you try to slow down, well, you basically take energy out from the orbit, so the orbit loses energy and it shrinks by however amount very, very slowly. So that's what happens with hot Jupiters. So basically, the orbit of hot Jupiter just keeps shrinking until they are eventually engulfed by the star. So that's the fate of hot Jupiters. But how efficient or how much does the orbit of hot Jupiter shrink is a question that we also don't know yet. And so this is what I'm doing. And to answer this question, I'm asking how periodic are orbits of hot Jupiters. So for example, if the orbit is shrinking, the first orbit will be here, but the second orbit will be like this, right? So to measure how periodic the orbits of hot Jupiters are, I would use the technique called transits that was actually brought up earlier. So we also do not have, instead of measuring the velocity or the wobble of the star, we can actually monitor the brightness of the star. And as a planet passes in front of the star, what happens is basically like an eclipse happening. And if we keep observing the brightness as time goes by, the brightness kind of dips as the planet is passing in front. And so we can just keep observing these transit events that we call them transit events. We can keep observing these transit events to measure how periodic the signals are. And so that's what I have been doing. Using the instruments we have on several telescopes around the world called the MOSCAT series. So we have 4 of our instruments, basically cameras, installed on telescopes in Japan, in Tenerife, in Spain, Haleakala, which is in Hawaii, and Siding Spring, which is in Australia. So we are observing the transits of exoplanets from telescopes all over the world. And this is, for example, what the data looks like for the transits of these hot Jupiters. We see that the periodic, the brightness of the star is dipping as the planet is passing in front. So I'm observing these dips to measure the periodicity of these hot Jupiter transits. And this is a preliminary result I have for one of the planets that I've been observing. And so on the x-axis, I have the orbital period of the hot Jupiter. So at the time of discovery, it had a slightly longer orbital period than what I have observed over the past 2 years with our instrument. So which means that the orbit of this planet might actually be shrinking, and we might be catching the very final moments of this hot Jupiter, which is pretty cool. And to put it in perspective, the orbit might be shrinking by 12 milliseconds per year, which is a very, very small amount, but the orbit is definitely shrinking. And if we can confirm this, it will be just the second discovery of such shrinking orbits. So I'm really excited about what we might find out in the near future. And I was also at Subaru Telescope, which is in Hawaii, to perform some observations to confirm if this signal that I've been observing is real. And this is a picture I have from the observation back in June. And so this is actually Tanaka-san, who helped me out with the observation at Subaru. And I have a cool story here because as he was taking me, before the observation, he was taking me around the telescope, and I got to walk around the catwalk of this telescope here, and he was showing me this thing right here. And he's like, this is a webcam that streams the night sky of Hawaii, if you know. And then I'm like, yeah, that rings a bell, right? So it was like a little dream come true moment for me because, yeah, 3 years ago I was at home stargazing during COVID, not even outside, just staring at my computer screen. But now I'm actually using the telescope to do actual stargazing for, astronomy purposes, and how cool can that be, right? So special thanks to Tanaka-san. And thank you for coming. That's my talk.
Sorry. We will have on the mic. It is just for recording. So yeah, please hold it and take it
Okay.
for recording.
If near the star there are Jupiter-like heavy planets are orbiting, so nearby Earth-like planets are safe.
Sorry?
If if in our solar system Jupiter are orbiting near the sun, so our planet Earth is safe.
So if we had, for example, in our solar system, if we had a Jupiter at an orbital period of 4 days inside the orbit of our Earth, would our solar system be stable? I don't know. The short answer is I don't know. But the fact that we do find these, sorry, the other way. Sorry. The fact that we do find these, hot Jupiters with friends here kind of suggests that the existence of a hot Jupiter does not immediately rule out or destabilize the whole planetary system itself. And we also have found planets outside, much exterior to our hot Jupiter. So these are orbital periods of less than 10 days or 1 day. But we also have found planets outside, maybe orbital period of hundreds of days, and they are stable. So I wouldn't say that they would immediately be unstable, but with how many planets there are in our solar system, it might be unstable. I don't know. Yeah.
So if we find the hot Jupiter, we can expect the biosignature.
If we find
Hot Jupiter. In that system, we can expect the biosignature.
Biosignature.
なんていうの
Uh,
The Earth-like planet is safe だと思って OK?
Basically, hot Jupiters, you cannot live on them, right?
No.
In the system. Oh, if you've had an outer small planet. I mean, if it's in the habitable zone, I think it's possible. Like
Possible.
the existence of hot Jupiter does not immediately rule out anything else. Yeah, I think. Yeah.
So, よかった。I'm glad.
Thank you. Any other questions? Okay, so can you hand it to
Hi. So since the Jupiter's orbit is the hot Jupiter's orbit are getting less and less every year. And from what I understand of stars is, the time it takes to reflect, the light to reflect back on Earth is, thousands, millions of years. So do you think you'll be able to see the effects of what happens the closer it gets to the sun? Or what do you think happens? Like, will the planet just disappear or,
Yeah. Eventually, the planet will disappear, but that would still take millions of years. So we wouldn't observe, for example, the system I've been observing. I don't think we'll observe the end of it in our lifetime. But we have also found, so other researchers have also found signatures of, for example, a planet that was
like
just
being
recently,
consumed?
consumed by a star.
Okay,
So there
thank
have
you.
been similar observations like that.
And the mass will be incorporated into the star.
Yes, I think so. Yeah, the mass will be incorporated into the star, and people have been thinking maybe like, if the star consumes that planet, will the star have enhanced, for example, elements that they received from the planet Yeah, and they've been trying to see all these kind of things, and there have been debates about if the detections they have for enhanced, basically distinct chemical compositions are real.
Just a follow-up question on that exact question. There is, if I remember, it's a Eastern European name, a Chiglinski or something like that, named star, where they find transuranic elements in the spectrum. They found absolutely bonkers things. And so first question is, do you know about this case? And two, so if I understand, another planet absorption could be a possible cause for the anomaly.
Huh. So I don't think I've heard of that exact case where they discovered.
They basically found transuranic.
I don't think I've heard of that exact paper or research, but I think the basic chain of thought in thinking about if peculiar signals come from the consumption of planets or not is the idea is the same. I don't know if they discussed that in that exact paper, but other similar papers do exist discussing peculiar signals if they can be attributed to the consumption of plants.
Okay,
Yeah.
Thank you very much.
Hello. Hello. It's very, very, very hard to understand. Because it seems to be you have observed several planets, right? That fit the definition of Jupiter's because they are hot, just because they are hot, right?
Mm-hmm.
So my question would be like, how many planets have you observed?
So how many planets have
How
I
many
been
Jupiters
observed?
have you observed in order to make a generalization?
So that's a very, very good question that I get asked by like my professors, and they'll be like, "You are looking at this one planet, and how is that significant? We have like so many planets, and is this one case significant to explain all the things that's happening for?"
If you have observed only one planet, then it would be fair to say, I'm observing this planet. This planet is called this and that, and this is what happens to him.
Yes. So that's a very valid point as well. But for example, the orbital shrinking, the orbital decay that I've been observing have only been directly observed in one particular case, and finding the second one would prove a point that one case was not specific to that one system, right? So I think increasing the sample size also still has some meaning to it, but at the same time, as you say, finding the trends in general using the whole population of planetary systems is also very important.
The answer being how many planets?
So I've been observing maybe about 10, and yeah, I do hope to find statistical. So about 10. Yeah.
And also I have a comment if possible. It's very hard to understand for us that we are not into the topic. But high eccentricity sounds very, very, very doesn't fit the meaning of the word.
Oh.
Because it's called high eccentricity. However, it's not arbitrary. It is only elliptical. So my question would be, why don't you just call it elliptical migration?
I think you can also call it like high ellipticity migration. It's just a name that we gave to it. And
because
to be fair, I think the mathematical term to explain how elongated the orbit is actually eccentricity. So
eccentricity meaning not eccentricity, but meaning something else, right?
So eccentricity in mathematics or in geometry refers to how deviant the shape of a circle or a circle
Like,
is
for example,
on a
ellipses,
scale of
right?
0 to 1.
Like ellipses?
Yeah. So an ellipse has a non-zero eccentricity.
Okay, sorry, I'm trying to understand.
Yeah,
I'm
it's just a term.
yeah,
I think.
thank you.
I assume the reason that the very first exoplanet we discovered was a hot Jupiter is because they have such. If our solar system was like a common example of them, I believe that like a hot Jupiter with like a rotation period of 4 days would be like really extreme case like this. But if we were like in the near future to like discover like a exomoon, like would they also be like really weird? Does they say like maybe like a perhaps like Earth size object like going around Jupiter maybe?
Yes. So thank you for the question, and this is a very good question actually, because if we look at the distribution here, right, and I've talked about only hot Jupiters, and I've talked about it as if that is like the most representative example of what an exoplanet is, but that is actually not the case. And actually, hot Jupiter only accounts for maybe like at most 5% of all exoplanets out there. And the reason that hot Jupiters were the first exoplanets to be discovered was because they were just so big. So the signals are, much bigger than what we would expect for a planet with only like Earth size. And the orbital period also plays a role, because if you remember the sinusoid, for a hot Jupiter, this complete sinusoid would only take about 4 days. But if you had to wait for example, for Earth, the entire sinusoid would take up 365 days. So it would be increasingly hard to detect, for example, planets that are smaller and also further out. So that's why we haven't found many of these planets out here. So the line that's carved out by the distribution here is not reflecting the actual distribution of planets, but it's just the artifact of our observational bias. That's what we call them. Yes. And for example, so what you mentioned about exomoons, and the answer is yes. So if we were to find the first exomoon, it would also have to be something that's orbiting close by and very relatively big, much bigger than our moon, for us to be able to detect it. So actually, the current efforts going on to find exomoons, they are targeting moons. They're talking about Jupiter-sized planets, and they're moons of Earth, like Neptune masses and things like that. So it's on a much larger scale of things. Yes.
Thank you.
The last question.
All right, thank you very much, Kawai-san, for the talk. So my question is maybe slightly out of topic, because what your research is about the transit and the orbits. But I have a question, very basic question about how does the hot Jupiter stay Jupiter? Because it is a gas giant, and if you get closer to a source of heat, you will either get burned or all the gases will be blasted away and you will be left with a core like Mercury. Do you have any idea about why the Jupiter stays gas giant even though it's very close to the star?
Yes. Thank you for the question, and that's a very good question as well. So the short answer to this is that they are close by, but not as close by, so that they face the risk of such kind of destruction. So the ultimate boundary for these kind of destruction to happen is what we call the Roche radius. So the gravity, basically the gravity of the star will outweighs the gravity of the planet that's keeping it all together. So the outer layers of the planet will just start to be stripped apart. And so say the orbital period of typical hot Jupiter is about 3 days. The Roche radius for these Jupiter planets exists on orbital periods maybe around.
Very short. So the Jupiter of our solar system is. Does it show what kind of migration, if we know?
So there are theories about how they have formed, and people think maybe they have actually migrated outwards after formation, and that's a completely different topic from this. But yeah, so that's all I can say.
Okay, so Hugo is still hanging here. So if you have another question, just find him to go. So thank you so much.